Hello, welcome to my channel. For those who celebrate the Lunar New Year, I hope you had a great New Year. This is the third episode of the BZ reaction series. The BZ reaction, also known as the Belousov-Zhabotinsky reaction, is a captivating chemical process exhibiting oscillating behaviors in a non-equilibrium thermodynamic system. It's a prominent example of a chemical oscillator where the concentrations of the key reactants undergo periodic changes over time, resulting in visually striking patterns. In the previous two episodes, we explored the only ferroin-catalyzed BZ reaction and the variation of BZ reaction involving both cerium-4 ions and ferroin. In this episode, we will discuss the BZ reaction without ferroin. But before we move on, here is a side-by-side comparison between the two variations of the BZ reaction. The reaction on the left only utilizes ferroin as its indicator, while the reaction on the right uses both ferroin and cerium. If you haven't seen the previous episodes yet, I would highly recommend you to see them first. Ferroin is a chemical reagent derived from the combination of a ferrous salt, which means iron salt with a +2 oxidation state, and 1,10-phenanthrolene. In the BZ reaction, it serves both as a catalyst and a visual redox indicator. In the first episode of this series, we have discussed its color-changing properties upon exposure to various chemicals with different redox properties. However, ferroin itself is a relatively expensive reagent to acquire. While its acquisition is not particularly challenging, its high price and the tedious preparation procedure limit its accessibility to a portion of amateur home scientists. It is important to note that most ferrous salts are not inherently stable over extended periods of time. Oxygen in the air would readily oxidize ferrous ions to ferric ions. Consequently, further purification is necessary to obtain pure ferrous salts to prepare the ferroin indicator for the BZ reaction. In Niall Red's video, he has to first purify the ferrous sulfate salt by performing a recrystallization and then combine the freshly purified ferrous salt with 1,10-phenanthrolene, which isn't exactly easy to dissolve in water. In my experiment, I opt to employ a slightly faster approach by just adding reducing iron powder to the ferrous sulfate solution in order to reduce iron 3 to iron 2. Subsequently, gravity filtration was employed before combining the resulting purified ferrous sulfate salt solution with the pre-measured phenanthrolene solution. The question arises, is it possible to conduct the BZ reaction without ferroin? This episode will explore this possibility in greater detail. During my research, I stumbled upon this intriguing article from the Royal Chemical Society website. This article introduces an alternative procedure that utilizes a manganese salt instead of the much harder to obtain ferroin and/or cerium for the BZ reaction. I've included a link to this article in the description below. Inspired by this approach, I've developed a slightly modified procedure. Instead of adding solids to the reaction mixture directly, I've made a change that allows for the addition of multiple solutions containing an equivalent amount of each reactant. This modification makes it easier to manage this reaction. Pause here if you like to take notes of the recipe. In this beaker, I've already pre-mixed 10 milliliters of solution A and 82.5 milliliters of solution B. Then we add 9 milliliters of solution C, which is mannolic acid, into the beaker. Once it's fully mixed, we will add 1.8 milliliter of solution D, which is 10% manganese sulfate solution, which will be the catalyst of this reaction. Upon the addition of manganese salt, we immediately observe a color change. In the next 10 seconds or so, the solution slowly faded. In this system, the color change is a result of the oscillation of the concentration of manganese 2 and manganese 3 ions. In a future episode, we will delve deeper into the detailed mechanism of the BZ reaction. For now, let's briefly examine this reaction. Manganese 2 has a faint pink color, but considering its concentration, it appears colorless in this demonstration. Upon the addition of manganese sulfate into the solution, the bromate ion in an acidic environment oxidizes manganese 2 to manganese 3, leading to a color change from colorless to reddish brown. It's worth noting that the literature reports manganese 3 as having a pink color, but this depends on the concentration, environment, and observer. Consequently, manganese 3 is reduced to manganese 2 by mannolic acid, resulting in color change from red to colorless. We will investigate the mechanism, mathematical aspects, and its scientific significance in a future video. After a while, the reaction has fully stabilized into a binary system, and we can observe the full range of color change from colorless to red. You are watching this video at a normal speed. The oscillation occurs every 9 seconds. Let's sit back and enjoy the magnificence of science. From now on, we are playing the video at 4 times the normal speed, so you can better appreciate the striking color change within each cycle. Let's now return to normal speed. Naturally, we wonder if we add more manganese catalysts, will the color change become intensified? Let's find out. In the same solution, we will add another 1.8 milliliter of the manganese sulfate solution. From now on, the concentration of manganese catalysts will be doubled. Let's wait for the oscillation to begin and observe the results. From what I can see, even though the concentration of manganese is doubled, during the red phase of the solution, the manganese 3 doesn't appear to have a deeper color. I could have obtained a more accurate results by using a spectrometer, but visually, there isn't much change in the color before and after we double the concentration of manganese. However, if you haven't noticed, the oscillation period became longer. Compared to the 9 seconds before, it now oscillates approximately every 20 seconds. So, for the remaining of this demonstration, Let's watch it at 8 times the normal speed. Another natural question to follow: can we replicate the reaction in a petri dish? I tried it, but since the color change between manganese 2 and manganese 3 is more subtle, the pattern formation in the petri dish is less noticeable and harder to observe compared to the previous runs with ferroin. However, we can combine both manganese and ferroin in the reaction mixture and compare the results with our previous runs. In the next video, we sequentially added acidified bromate solution, mannonic acid solution, and sodium bromide solution, and waited for 10 minutes for the solution to become colorless. This part follows the same procedure as the petri dish demonstrations in the previous episodes. After the solution becomes colorless, we added several drops of 10% manganese sulfate solution followed by 1 milliliter of the ferroin solution. A beautiful pattern has evolved. Compared to the ferroin-only version, the waves appear to be thicker. As the reaction nears its end, we can observe the formation of the brown manganese dioxide in the lower corner of the petri dish. This is significant because in the busy reaction with only ferroin or the ferroin-cerium system, no solid formation was observed at the end of the reaction. You are now watching a side-by-side comparison between the busy reaction with cerium ferroin on the left and the manganese ferroin on the right. That concludes the video for today. For those who stayed through the entire video, here is a bonus for you. Here is a peek of the footage of an upcoming video. It takes a lot of time and effort to make a video like this. If you are intrigued by this video, please feel free to like, subscribe, share, and comment so I can make more videos like this. See you next time!